We find ourselves at a bit of an intriguing point in the life cycle of HS1. Though often still regarded as a new railway, we're on the brink of our 22nd year operation. This shift means that several of our asset classes are reaching the end of their life cycle and creating a growing need for refurbishment and renewals. So today, I'd like to share my experiences with the deterioration and renewals capability. I'll try and outline how we've utilised a well-structured system to effectively manage our ageing assets while addressing the challenges of deterioration. So, essentially, we are a 60-odd mile siding built on a French infrastructure model. We are the only high-speed railway in the UK. We maintain, inspect, renew the infrastructure on behalf of HS1 Limited, who have the concession from the government to own and operate the infrastructure. We have very dense and complex S&C at St Pancras. We have long slab track tunnels. We have ballasted open stations, steep gradients, high cant and cant deficiency. As a high-speed railway, it generally breaks most of the design rules thanks to all the vertical and lateral curves and the fact that we head north, then hang a left, and then head south to park up at St Pancras. And did I mention we are the only high-speed railway in the UK? The concession structure, coupled with the direct correlation between renewal expenses and access charges, provides us with the opportunity to adopt a longer-term perspective compared to others. This allows us to justify investments if they offer comparable value for money, yet we must remain focused on ensuring rail travel remains both affordable and accessible for our customers. We need to build a solid business case for the CP5 determination. Ours is different to yours. Bear that in mind. It's actually a CP4 determination. It's a bit of a typo there, so I apologise. Instilling confidence in HS1, our customers and the regulator that we are making the right decisions at the right moments. This includes demonstrating sound asset management practices to optimising value over a 40-year horizon. Given that many assets are of a similar age, our plan must be carefully structured to distribute demand efficiently, avoiding wasted asset life while ensuring that final asset is replaced just before it reaches the end of its life threshold. The challenge lies in balancing optimal asset performance with maximum availability for our customers, which necessitates conducting these activities with minimal access windows. Although these expectations are reasonable, achieving them requires a delicate balancing act, supported by a well-planned approach. We have developed and are still delivering our CP3 plan, which includes building expertise in high-speed switches and crossings, replacing RT60 metalwork at St Pancras, rail replacements, and hopefully soon ballast refurbishment. Our CP3 plan has preserved asset performance, but we remain committed to continuous improvement. Striving for a better balance between cost and availability, especially in these challenging times for the industry, the plan was initially formulated based on manufacturer requirements and recommendations and industry best practices. However, we've discovered that these guidelines don't always align with the real-world conditions. Additionally, our original track asset age was measured in years rather than usage, leading us to plan renewals based on anticipated lifespan rather than actual utilisation. This approach resulted in some assets being replaced prematurely. As we began to adjust our strategy, we looked into industry models like Vitism, but found they didn't align well with our needs, mainly due to the differences in our maintenance philosophy and the consistent quality of our construction standards. Given that high-speed lines are relatively new, with the oldest around 40 years, no established industry model exists, as they haven't yet completed a full deterioration cycle. Adding to the complexity, we are a mixed high traffic speed line, with more extreme geometry making our wear patterns less comparable to those of the European operators. In a sense, we've been somewhat on our own, navigating as best we can. Throughout the control period, we've validated our renewals plans against asset conditions, allowing us to adjust expected asset life accordingly and refine our strategy to be more than just it's old, so replace it. However, this also meant that some assets were kept longer than they should have been, as they weren't included in the initial plans. We knew we had a significant amount of data which had been gathered through our inspection and maintenance processes. And this data was becoming more valuable as our inspection teams enhanced their skills. By aggregating more relevant information such as tonnage and wear rates from dimensional inspections, we could better understand how the asset was performing and where it stood in its life cycle. A previous head of engineering for track at high speed developed a modelling tool, that allowed us to predict a progression of the asset life cycle, helping us determine the optimal renewal timing. He identified key factors influencing deterioration, including design, geometry, both vertical and lateral, environmental conditions, so single bore tunnels, viaducts, overbridges, underbridges and earthworks, and track quality. Assessed through long wave ride quality and short wave defects, rail wear, rolling contact fatigue and rail defects, with the frequency of defects and related closures and welds significantly impacting the high-speed geometry. We also examined how maintenance activities, particularly tamping and grinding, could reduce the asset's lifespan despite their role in maintaining performance. Each data set was standardised to allow consistent integration into the model, making updates straightforward. This information was then overlaid with asset utilisation metrics, examining how much tonnage and what speeds the infrastructure have been subjected to. Our extensive historical data provided a precise model of which trains traverse specific sections. All of these factors were correlated with appropriate weightings assigned to their relationships. The model was designed to be adaptive, enabling us to incorporate new insights and adjust parameters as our understanding of asset behaviour deepened. Additionally, it was built with flexibility to include new data sets as they became available. Once the model was developed, we could translate these projections into target renewal years based on expected traffic volumes and our maintenance strategies. Naturally, the raw outputs were initially quite irregular, with localised interventions leading to early renewals. However, we managed to smooth these projections by focusing on targeted solutions to address the root causes instead of opting for full-scale renewals. Once we established the realistic demand forecast, we further refined the work schedule to maximise efficiency. We explored the use of production line approach for renewing extended sections of rail, sleepers or ballast, even if it meant removing some still serviceable components. The goal was to strike the optimal balance between maximising asset life and achieving production efficiency, such as replacing rails slightly earlier to align with sleeper renewals. Additionally, we created buffer zones around high-speed S&C to ensure that the transitions were not disrupted by adjacent works. This strategy also enabled us to adapt our maintenance requirements to support the desired asset lifespan. So what is delivery integration, or what do we call it? We've heard a lot about it today, and this is a model that we've been working towards. So my summary is that we look at the big picture to get most from our resources in the least disruptive way. First of all is the axis. When can we get onto the railway and what's the optimal window? What do our operators and customers need, and is there a seasonal demand? So, for example, we have an issue with, well, it's not an issue, customer Eurostar want to run additional trains during January for the snow season. We have to take those things into consideration. Do we need one line or both? And for how long do we want it? What restrictions do we need to place in afterwards? So speed restrictions, etc. Do we need prep and follow-up shifts? Do we have enough people to efficiently set up the possessions and isolations? Once we have possessions secured, how do we get on the railway? We're fortunate to have well-designed access, but which are suitable for people and plant? How do we get materials to site? These accesses are well-designed, but they're fairly well spaced at approximately 15 kilometres apart, with smaller accesses in between. What can we bring in by rail, and how do we get machines onto the track? What about our line-side neighbours? How do we minimise the disruptions to their lives, and how do we keep them well informed? This extends to environmental considerations as well. So how do we avoid damaging or disrupting any habitats? Then we look at our different disciplines, both as a risk and opportunity. While we were renewing the track, what signalling and OCS equipment needs to be removed and reinstated? Will our work affect the positions of the track, and do we need to adjust contact wire positions? Do we need isolation for the work? Do any of the assets we've taken off need replacing with new ones? As the teams are already on site to support track delivery, can we use them to deliver any renewal work for their own discipline? Do our civil engineering colleagues need access for their assets, and is it efficient to do so? We have structure joints, for example, that can only be maintained once the track is removed, so we need to take that into consideration as well. Once we know what's needed, how do we do it efficiently? For instance, can we use mechanised solutions, or do we have to stay with manual stuff? Zip through a couple of those. Didn't realise I put so many on there, actually. We've identified correlations between maintenance activities, traffic load, and asset deterioration. However, it's crucial to continue to update these relationships as the assets age to maintain their accuracy. For some assets, like a slab track, which are still in the early stages of their life cycle, it's essential to establish effective monitoring systems and leverage technology to closely track the wear. Improving data quality through electronic forms and automation can enhance reliability and consistency. Additionally, optimising access windows and working times will be vital for delivering maximum value for money and ensuring high customer satisfaction. Reducing the duration required for possessions and isolations will be increasingly important as we move to CP4, where, like many others, we must find efficiencies to accommodate tighter budget constraints. The current ballast refurbishment plan covers 30 kilometres. Originally, it was due to start in 22-23 at a rate of 10 kilometres per year. This was driven by deteriorating track geometry, necessitating annual tamping and frequent manual hand packing at heavily used sections, with some sites tamped over 20 times and hand packed over 50 times. The ballast, which is of substandard quality due to initial construction constraints, is now 22 years old and facing extreme alignment challenges similar to those found on the LN3 Paris to Calais line, where SNCF began refurbishing at 22 years. Delays in action risk increased operational costs, enforced speed restrictions and public dissatisfaction due to rough rides. However, we have found it difficult to engage with the market in high output ballast cleaning, due mainly to our small fish in a big pond status, and that most of the market is European. We've had to put mitigations in place to ensure we retain geometry quality that we require for the high-speed tracks. Those mitigations are the usual stuff, so they include intensified tamping activities, but they cost us over £1 million annually. Though this accelerates ballast degradation and may necessitate speed limits for safety. Delivery challenges include securing specialist equipment, access and staff approvals. Addressing these issues promptly is crucial to minimise risks and maintain operational efficiency. So how do we ensure we are only replacing what we need to replace without actually replacing everything? In order to do in order to be assured that we are treating the right sites and removing the right ballast, not removing any more than we need to, we needed to utilise not only our conventional means of track and ballast assessments, but also utilise new and less invasive technologies. Traditional renewal techniques require ballast core samples to be taken at periodic intervals to assess the ballast and the track bed condition. This was something we wanted to avoid, and so the search for an alternative was undertaken, and a company called Sol Solutions seemed to do what we were looking for. Essentially, Pandascope is a metal tube with regular slots in the side at 5 millimetre spacings. An endoscope is then fed down the tube and the image is recorded digitally to give real-time images. Results come through in a matter of days rather than weeks, and that would be experienced from conventional core samples, and this significantly less intrusive without the need for test holes to be dug and additional resources and possession times. So, try and get this laser to work, this video to work. I'm not sure, how do I do that? Is that it? There we go. So you can see, as the camera goes down the tube, you can see the degradation of ballast. It starts off fairly angular, where it's in between the cribs, but as it gets below the sleeper level, it starts to become rounded. As it comes further down, you'll start to see where the fines generated from the attrition start to build up, and further still, it gets to the point where it's fairly well contaminated, and this is usually about 600 to 700 millimetres below surface level. So coupled with the impact resistance graph, this becomes a powerful tool in helping us to understand our track bed conditions without digging invasive test beds or taking core samples. Some of our ironwork, both on the high-speed section and at St Pancras, has shown significant signs of wear and deterioration. St Pancras is predominantly due to the S&C geometry. Remember I said our line broke every rule in the book. Well, St Pancras is a prime example of that. We have short radius curves, S&C on vertical curves and transitions, low speed inclines, and S&C on floating track slab. All of these factors, coupled with a P12 and S2001 wheel profile and some very stiff vehicle dynamics, mean we have a very high deterioration rate, high levels of plain line wear, corrugation, and switch blades that you could shave with. Replacing these assets with what was an immature track and planning team was a challenge. Initially, re-railing, which on the conventional railway would have taken anywhere between 4 to 6 hours, had to be taken in a long block over a Christmas period, and due to tight clearances, had to be installed with TRT units, which the team had never worked with before. So that meant fostering an effective relationship with McCulloch Rail to ensure we could deliver over a Christmas period. Switches and crossings have to be planned meticulously to ensure they are installed efficiently and correctly. Our Schedule 8 payments are significantly higher than the conventional railway. A 5-minute overrun for us is very expensive, so everything has to be planned in detail to the minute. Unexpected issues such as world runouts have a huge financial impact, not to mention the reputational damage that the fare-paying customer perceives. Oh, gone a bit too far there. That one. No, that's it. High-speed switches are another challenge altogether. Installing a 1 in 46 switch that is around 42 to 45 metres long was a huge undertaking. When we first started replacing our high-speed S&C, we were using Kirovs. This was expensive and unsustainable. After the need to replace one of the switches at short notice due to defects, we had to find a more cost-effective and more readily available solution. So we moved towards using the TRMs, which are basically sitting in Balfour Beatty's yard doing nothing. So we cross-accepted them through our SLP process with very few modifications to use them on our network, and now we use them not only for our high-speed switches, but also for our swing nose crossings. They are cheaper than Kirov, and because they are underutilised on the conventional railway, they are more readily available. Thank you for bearing with me. You'll be glad to hear I've nearly done. But before I do, I'd just like to briefly highlight a few key points. First, we recognise that reverse engineering 2 decades of historical data was no small feat. Ensuring that information is recorded consistently and comprehensively will greatly simplify future analysis. We've successfully tracked nearly every vehicle that has travelled on our network, which is crucial for predicting the effects of timetable changes, increased line speeds, wear rates and associated costs. Including customers and stakeholders in our processes has proven invaluable, particularly in negotiating access and exploring better ways to operate. Understanding what drives their needs allows us to think creatively about how we deliver our work. By implementing a structured preventive maintenance strategy, we can optimise asset performance and make wear patterns more predictable. However, it's essential for us to maintain self-critical and continually ask, what can we improve? Thank you very much for your attention, and I hope you haven't missed any trains.